So today we're going to do a problem from worksheet number 7 of the Academic Excellence Workshop, and it's number 2. So basically what's happening in this problem is we've got this potential energy function that depends on x, and we say that this potential energy function is acting on some particle, and we're going to assume that that's the only thing acting on this particle. And then we're given one more piece of information. We're told that this particle is at rest at this x value of 3 meters or whatever. And we're asked to find what is the kinetic energy at equilibrium position. So a good first step to this is to say, well, what is the equilibrium position? So we remember that equilibrium positions are wherever the force is 0. And the force, to get that from a potential energy function, is just to take the negative spatial derivative. So we'll say f of x equals minus ddx of u of x. In that case, that means minus, and then I get 2ax plus b, which took the derivative. And I say, well, at equilibrium, that force equals 0. And I solve for x, and I get x is minus b over 2a. That's x equilibrium. So now we're here, and so we say, okay, this particle is only acting under the influence of this potential energy. And the only other type of energy that's going to change, because it's just a particle moving, is kinetic energy, kinetic translational energy. You know, it's a particle, so it can't rotate, it's a single point. And none of the other ones make sense either. So we're just going to say that work is equal to change in energy. And we're going to say that the work done is 0, because we're just going to put the potential energy, whatever's causing it, into the system. We're going to say 0 is delta k plus delta u. So I know, I'm going to move this down here, I know that 0 now equals k final minus k initial plus u final minus u initial. And so the u's are actually really easy. First I'm going to pick an initial and final time, and it makes sense since I know about 3 meters, I'm going to make that one of the times. And since I want to know stuff about equilibrium, I'll make that one of the times. So I'll make x equals 3 meters my initial time, and I'll make x equals equilibrium position my final time. And so I'll say, what is kinetic energy at the final time? Well, that's what I want, so I'm just going to leave it like that. So I'm going to say k final. And then I'm going to say at the initial time, it told me it was at rest. And so it's actually really useful. So that goes away. U at the final time is U at equilibrium. Well, I've got a function that depends on x, and I've got an x value, so why don't I just throw it into that function and find out what U is? I'm just going to say plus U at 3 meters. Oh, sorry, equilibrium rather than 3 meters. So that's U at x eq. And similarly to what I just said, the initial time is at 3 meters, so I'm going to plug in U, plug in 3 meters. And if I plug all of this stuff in to this equation and plug it in here and stuff, I should get, and plug in these two values right here, I believe I get that the, oh, sorry, this is a longer pause than I wanted right now. We find that the kinetic final equals 28.125 joules.